This is chapter 4 in McDermott's Physics and Technology of Radiation Therapy, second edition. We're going to be looking at X-ray production. Up to this point, we've been learning a little bit about photons, what the energies of these photons are. What we haven't really looked at so far is how to go about generating them other than through an unstable atom. So this is where we start to learn how at least the low energy photons are produced in order for us to be able to produce usable X-rays that we can use in medicine. So as you're probably aware of, X-rays, of course, were discovered by Wilhelm Conrad Röntgen in November of 1895. Changed a lot of people's lives, including his own. There are two main purposes. You've got diagnosis and therapy. And what we're going to be looking at in this chapter is going to discuss the diagnosis side of things. The therapy we will leave for other chapters, but X-ray photons generated for diagnostic imaging studies typically have energies in the range of 10 to 50 keV. Therapeutic X-ray photons have energies in the range of 50 keV up to 20 MeV. And this is why we went over changing units and what the prefixes meant. So you can see here the 10 to 50 keV is kilo electron volts. When we start saying MeV, then we're referring to mega electron volts. So let's take a look. If we're looking at the low energy X-rays in an X-ray machine, we've got two major components. We've got the X-ray tube and the generator. And the X-rays are produced inside the tube and exit through the window. Now we'll see a little bit more about this here. We've got basically our X-ray tube here. We have a current that is flowing here in order for us to be able to get electrons boiling off of this particular filament. This running through here is going to be called the cathode. When the electrons are released from the filament, just simply because they have enough energy to be able to escape from the current or for the wire through thermionic emission, they are let go. Now, what happens is that you have a potential difference or a voltage in between here and here. We take advantage of that because once the electrons are hot enough, they have enough energy to boil off, they're going to want to go in a particular direction. And so the voltage is what says, hey, come this way. So the electrons boil off and boom, they go over here. Now, when they hit here, they're going to hit most likely a tungsten target. There are other types of targets such as molybdenum, but in general, you're going to be looking at something like tungsten. It has a high Z value and it can cool off more quickly than other elements can. So that's why we use it. Once it comes here and hits this target, you see a slowdown of these electrons, and that slowdown causes energy in the form of photons to be emitted. And the ones, they're pretty much emitted in any direction, but they're going to get stopped by this or that, stopped somewhat by the target itself, maybe through some of the material around the target. Maybe they're stopped by this housing that is around the X-ray tube that's lined with lead. There's a whole number of things, but anything that will escape through this particular window is what's going to be usable. That's what we can use in order to be able to take pictures of something else. So you can see more discussion about this. The cathode, which is the side that's going to release the electrons, the anode, which is going to receive them. You can see here from the work energy theorem that we have a quantitative relationship between the work done on an electron of this charge when you accelerate it between the electrodes. The final kinetic energy is going to be the amount of work that is done on that particular charge, which is going to be the same as the charge multiplied by the voltage. And so the charge here, of course, being E multiplied by the voltage, electron volts, this is going to be energy. This is going to be the amount of kinetic energy that they gain. Well, that amount of energy, if all of it were to be used up in a single event of an electron slowing down, then the photon, the maximum energy of a photon being emitted depends, of course, upon its frequency, or C over lambda, which is this relationship sort of turned around due to the frequency multiplied by the wavelength will give you the speed of light. So we can see here the minimum or the maximum frequency is going to be the same as trying to get the minimum wavelength. So the number of X-ray photons created in the target is proportional to the number of electrons striking it. So this in turn is proportional to the electric current through the tube. So twice the current will lead to twice the number of X-ray photons released. Obviously, you want to be able to have a current high enough to produce an X-ray beam that's actually going to be usable to tell you the contrast of what it's striking as it goes through, let's say a patient or whatnot. And through that, you can be able to tell or have a better idea as to what's going on. So the potential difference of the voltage across the tube may not be constant in time, and it depends on, of course, the design of the X-ray generator. The electrical current supplied by the power company is going to be AC, or alternating current, where the current and the voltage oscillate back and forth in the wires with a frequency of 60 hertz. This contrasts with direct current, which is a current that always travels in the same direction. X-ray generators have a circuit called a rectifier, which basically converts AC into DC, and there may be some residual ripple in the voltage applied to the electrodes in the X-ray tube. Newer X-ray machines have higher frequency generators that produce minimal ripple. And the potential difference across the tube is usually quoted in terms of the maximum value of units of 1,000 volts. In other words, KeVP, short for kilovolts peak. It can range anywhere from 20 to 300 kVp. The kilovoltage is not the same thing as the kiloelectron volts. They're different units. Voltage is a measure of potential difference. KeV is a measure of energy. Those are not the same concepts. Diagnostic X-ray machines utilize a potential difference ranging from 20 kVp up to about 120. And there are three classes of therapeutic X-ray beams. In other words, if you're dealing with photons of this energy, there are going to be three different types of beams. You've got superficial, orthovoltage, and megavoltage. Superficial X-ray beams have two potentials between 50 and 150 kVp, and they're used to basically to they won't penetrate the skin very much. Orthovoltage beams are produced by two potentials between 150 and 300 kVp, and megavoltage beams are produced by linear accelerators, and we'll get into that. Linear accelerators are going to produce X-ray beams by accelerating electrons through an equivalent of a potential difference of 1 million volts. This is a picture of a superficial therapy X-ray machine. And so in this chapter, we're going to concentrate the attention on the technology for producing diagnostic superficial and orthovoltage. We'll get to the other later on. This is an example of how a source of X-rays or a focal spot is used to image an object by casting a shadow onto the image plane. So you got your focal spot here, you've got the object that's being imaged, so you got rays coming out of here, and they're going to strike this image plane. The red lines originating from different locations within the focal spot. A large focal spot will lead to significant blurring because the bigger you have here, the bigger the penumbra down here. And if the source is tiny, the blurry edge region will become much smaller and the image will be much sharper. So the region of the target from which X-rays are emitted is called the focal spot. And you have to have a trade-off because a small focal spot will produce intense heating. And while you can get a very fine picture of what's going on, you still have to get rid of the heat. Otherwise, this is going to melt your target and you're not going to be able to see any pictures anymore. So you have a trade-off of how you get rid of the heat and the ability to be able to produce better pictures. So the apparent focal spot size can be made smaller than the actual focal spot size by tilting the target at an angle. So this is one of two technical tricks that you can use to deal with the heating, as well as reduce the apparent size of the focal spot. So the apparent focal spot is the size of the focal spot seen by the film. And it's called the line focus principle. If the actual focal spot size is S and the target angle is theta, then the apparent focal spot size is this. Now let's see, it mentions figure 4.4. So you're seeing it here. The line focus principle. So the apparent focal spot size S can be made smaller than the actual focal spot size big S by tilting the target at an angle theta. So the insert or the circle here shows the geometry used to find the relationship between S and S, which is what this is talking about. Diagnostic tubes use an angle between 6 and 17 degrees. Superficial therapy tubes use an angle of about 30 degrees. For diagnostic applications, the apparent focal spot ranges from 0.1 times 0.1 millimeters squared for mammography and up to 2 times 2 millimeters squared, depending on the design size of the tube. So a particular X-ray machine may have two focal spot sizes available. The two focal spots are produced by the use of two different filaments. The operator chooses the focal spot based on the image detail needed and the expected heat loading of the tube. So for therapy treatment applications, a small focal spot size is not as important as focal spot sizes ranging from 5 to 7 millimeters squared. So tilting it is one way to be able to deal with having a smaller focal size, as well as being able to dissipate the heat. A second strategy is having a small, is to make the anode in the shape of a disc and then to spin the disc. And that's this. Both of these anodes have the same apparent focal spot size. The stationary anode has a target of 4 millimeters squared, whereas the rotating anode has a radius of 30 millimeters and a target area of 754 millimeters squared. So the heat energy is spread over an area 200 times larger than for the stationary anode, than what you have over here. So the sound of the spinning rotor can sometimes be heard as a whine from the tube housing. Uh, there is a variation or gradient in X-ray intensity in going from the anode to the cathode. This is known as the heel effect. So in other words, looking at this, um, the heel effect is pretty much that you have more dissipation of photons through other material as it goes through here if it appears on this side as opposed to over here. So the intensity is lower on this side rather than this side. They call this the cathode side because it's closer to the cathode. This obviously is further away. You can see here you've got a rotating anode X-ray tube. You got your rotor in here, which is going to turn the target here. So a very small fraction of the energy of electrons, usually about 1%, I think, is converted into X-rays, which exit the tube through the window. So it's horribly inefficient, but that's what we got. You can see here this protective housing that is around here reduces the radiation leakage, letting some of it go through here because when it strikes the target, these things go everywhere. You can't control exactly how this is going to look, but what you can do is you can weed out the stuff that's going to be detrimental to you. So if you're going to be close to the machine, you want some shielding on there to protect you. So the design considerations for an X-ray tube for superficial or orthovoltage therapy are different from those of diagnostic. Therapy tubes do not have a rotating anode, and the focal spot size is not critical for therapy, and therefore these tubes have a larger spot size. The instantaneous heating rate is going to be lower, so these tubes are designed to be run continuously for a relatively long period of time. Newer therapy tubes are compact, water-cooled, and constructed from metal and ceramic. Therapy tubes with electron beams having energies above 200 keV have a hooded anode, and at these energies, the primary electrons that strike the target eject secondary electrons from the target material. So let's just go to the summary. They have a larger focal spot size than what you see in diagnostic. The anode does not rotate, and you've got a hooded anode above 200 keV. And that's what the third part there is. Having energy if a hooded anode as in 410. So let's take a look at 410. So you can see here the earthed anode, which is what it's talking about here. So high voltage cable comes in from the left. The araldite rubber and ceramic materials provide electrical insulation. The target is tungsten, embedded in copper, and the anode, which is grounded in water, is water cooled. So nowadays, you've got more digital imaging going on than what you used to have, which is people running back and forth to the X-ray room to develop the images and make sure you are on target. So the X-ray film consists of a plastic base that is coated on one or both sides with an emulsion of silver halide crystals. The film base is made from a blue tinted translucent plastic. It is designed to be flexible and relatively transparent, and the emulsion is a silver halide, a compound that is 3 to 5 micrometers thick. The film is used in radiation therapy departments. It's usually 14 by 17 inches. So film is not an efficient means for detecting X-rays. When a piece of film is exposed, most of the X-rays go right through the film without making any change to it. But it is very sensitive to visible light. And diagnostic X-ray films are used with an intensifying screen. This converts some of the X-ray energy to light, which in turn exposes the film, and the film is placed inside the cassette that has an intensifying screen built into it. The film type must be matched to the screen used in the cassettes. The use of a screen reduces the radiation dose to the patient and shortens the exposure time. The purpose of the screen for megavoltage therapy is somewhat different, and we'll get to that later. So you can see the cassette here. You put the film in and you shield it from outside light as best you can. And what you have here for radiographic film is a base, and then you have emulsion on either side. Radiographic films are shadow pictures we've already seen due to the non-zero focal size spot. These shadows can be blurred. In addition, image contrast is degraded by radiation scattering inside the patient, which is not much you can do about. Radiation scattering occurs when the direction of travel changes as a result of interaction with matter. Radiation that is not scattered in such a fashion is called primary radiation. So you can see here that you have a source goes through a patient. These electrons or these photons go through, they interact in the patient. And some of these things get scattered. The idea of the grid is to take out the scatter and leave as much of the regular primary beam to come through. You can also see here a paralleled radiographic grid is designed to increase the contrast. The diagram shows the typical dimensions here. So film is not really something that, at least in therapy, that we use a lot like we used to. It's been replaced primarily by nowadays digital radiography. You have had computed radiography before, and it is a direct and easy replacement for film. It involves using photostimulatable phosphors housed in a cassette. When it's exposed to light, a small fraction of the energy is stored in the phosphor. The CR system uses a scintillation screen to convert X-rays to light. After the cassette is exposed, it has to be processed in a reader. The phosphor is read by using a laser. Exposure to the light of the laser causes some of the stored energy to be emitted, and the light enters a photomultiplier tube, which converts the light energy into the analog electrical signal. And digital radiography does away with the processing step. Digital detectors employ thin film transistors, TFT, array detectors. Exposure to light causes a charge to be stored in the detector. After the exposure, the detectors are read out. So there are two schemes for detection, indirect and direct. For indirect, a scintillator panel is used to convert the X-rays to light. And you can see some of that here in figure 415. As soon as I can find figure 415. Which apparently I can't. Let's see. No, wait. There we go. So you've got aluminum, you've got an air gap, you've got a CSI scintillator, you've got attenuator and photodiodes. So that is an Electa 16 kilovoltage uh, imaging panel. So an X-ray generator supplies the needed voltages and currents to the X-ray tube. It must supply enough voltage to accelerate electrons between the cathode and the anode. Generator has to supply current to ensure that a sufficient number of electrons cross the tube so that the intensity of the X-ray beam will be adequate. So to make a radiographic exposure, you've got to have three fundamental quantities that are set. You've got the tube voltage measured in kVp, the tube current in milliamperes, and the time of exposure, usually in seconds. So a good quality radiograph depends on the proper choice of these values. This combination is often referred to as the technique. So for an example, an AP abdominal film on a particular X-ray unit using a specific screen film combination, the technique might be 80 kVp, 200 mA, and 0.4 seconds. The current through the tube is expressed in units of milliamperes and is directly related to the number of electrons across the tube. The length of time that the tube emits X-rays is set at the generator console. The units are expressed in seconds. A typical radiograph might require a few tenths of 1 second. Longer time exposures risk blurring from patient motion. So the output is proportional to the number of X-ray photons produced. The degree to which the image blackened by the X-ray is related to the output. So the MAs for the abdominal film mentioned above is 200 MA times 0.4 or 80 milliampere seconds or mass. Current and the time can be changed independently of one another. However, if the product remains the same, the X-ray output is going to remain the same. So assuming that the kVp stays the same, we get that result we talked about. But what happens if we change it? And there's really no simple answer. The number of X-ray photons is sensitive to this kVp value. A small increase leads to a large increase in output. So we can see the proportionality here. So we've got a lot of factors here that we have to take into consideration for each individual machine. So an alternative to completely manual settings is the use of the AEC, and then the X-ray machine measures the amount of radiation passing through and terminates the exposure when the amount is sufficient to produce an acceptable degree of darkness on the film. With heavy use, overheating of the anode tube and tube housing become a threat. An X-ray tube can be ruined by overheating, and there's a limit on the heat deposited in the anode by a single exposure. If that's exceeded, then the heat production can be sufficiently high to cause some melting of the target and the focal spot, and you don't really want that. So a typical example of a limit for a single exposure is at 120 kVp. The current should not exceed 400 mA for a large focal spot. The anode cools the housing, or the tube and the housing can overheat depending on the number of exposures, time between them, and the technique. And so here you have a chapter summary of the concepts. I would encourage you to go through and look at those. And then we'll get to the problems in a different video.